important.
All right. Good evening, engineers. Magandang gabi. Thank you for joining us again for another edition of Even Learning. Thank you for joining us today. This is the first for our training session today. This is the first of ACMV fundamentals. I just want to check if you guys are hearing me okay. Do you guys hear me okay? If you guys do, give me a heads up, thumbs up. There you go. Sir Dennis said it's okay. So I'm assuming everything's okay now. All right. Again, this is the first of our ACMV fundamentals. This is actually a three-part series. Okay. This training is brought to you by Even Learning. Even Learning provides quality trainings and seminars conducted by your peers. For tonight, we will be starting off for this new series with psychrometric analysis for AC systems. We will discuss about thermal properties of air, how to use a psychrometric chart, and perform some psychrometric calculations. This training is expected to last for about an hour, including the question and answers. As we go along the training, you may have, if you have questions, feel free to write down on the comment sections here on Zoom or in Facebook. Or you could email us at evenlearning.sg@gmail.com. Should your questions remain unanswered, drop us a mail, drop us a note, and we'll get back to you as soon as we can. Okay, so I will share my screen. Oops. All right. Okay. Oops. There you go. All right. Again, we are starting with our ACMV Fundamentals series using Psychrometric Analysis as our first of a series. So the second portion is air handling units, and the third portion will be pumps and fans with the dates given on the screen. So we will start with Psychrometric Analysis. My name is Donnie Gabriel. I am a professional mechanical engineer specializing in ACMV. I will be your instructor for tonight. I have more than 20 years experience designing, constructing, and managing projects related to ACMV. You can find me, you can reach me anytime at evenlearning.sg@gmail.com, or you can drop me a line on my mobile. My mobile is 9389-5128. Right. Okay. So for tonight, we will be studying 3 topics. First, the thermal properties of air, the use of psychrometric chart, and the psychrometric process, and we will perform some psychrometric calculation. Okay, first, psychrometrics. What is psychrometrics? Psychrometrics is the science involving thermodynamic properties of moist air, the effect of atmospheric pressure on materials and human comfort. The definition is normally broadened to include method of controlling the thermal properties of moist air. So take note, we are dealing here with moist air. So in the thermal properties of air, what are their properties at given places, given situations, and how will they react and how will they behave if we manipulate some of those conditions. The properties of air here is usually measured at sea level. So this is our standard measurement, no? Measured at sea level. The standard temperature of air we will be defining as 20 degrees Celsius. So if the temperature differs, so for example it's 21, all the parameters will also change. However, since the changes are minute and we can consider insignificant, so from 20 to 30 to 40, we will assume that all the parameters are the same. Even in the pressure at 1 atmosphere, 101.325 kilopascal, we will assume at same atmospheric pressure measured at sea level, measured at altitude of Singapore, altitude at Philippines. We will assume everything is the same. Because the changes are so minute, we can consider it insignificant. So at a standard level, sea level, the standard properties of air is 20 degrees Celsius at 1 atmosphere, 101.325. Specific heat is 1.005. So we'll just say 1 kilojoule per kilogram degree Kelvin. Latent heat of vaporization is 2465 kilojoule per kilogram, and the density of air will be 1.2 kilogram per cubic meter. Again, this is our standard air. If you want more, if your calculation requires more accuracy, you can change your parameters based on your location, based on the location of when you're dealing with. But since we're dealing with air conditioning system, we will be basing all our calculations on the standard measurements of air. So this is a standard measurement of air. Psychrometric chart. So what is a psychrometric chart? Well, the psychrometric chart here plots all the parameters or all the properties of air in a graphical form. So you can see there's lots of lines there and there's lots of numbers, and we need to make a sense of what we are seeing. So we will define first the lines that we are seeing in the psychrometric chart. Okay. So here, you could see here the curvy line on the psychrometric chart is defined as the relative humidity. So this is the amount of moisture inside the air at a given volume. So for example, if they say 50% humidity, which means 50% of the amount of air is equal to the amount of moisture inside the air. The diagonal line, you can see there's two sets of diagonal lines here. The first set of diagonal line here is called the wet bulb temperature. What is the wet bulb temperature? A wet bulb temperature is the temperature that you get when you measure the air using a saturated or a wet wick. Ano yung wet wick? When you see in the end of the thermometer, there's the bulb, right? There's a bulb. So if you cover it with the wet cloth, or you make it saturated, which means the humidity will be 100% because it's saturated with water. And what temperature you will get, that is the wet bulb temperature. The bulb at the thermometer, you put a wet cloth, signifying it's 100% saturated water, and you will get this temperature. So that is a wet bulb temperature. If you take out the wet cloth, it's dry bulb temperature. So when the air is not saturated with water, it's called dry bulb temperature. If the air is saturated with water at 100%, it's wet bulb temperature. Okay? Wet bulb, dry bulb. So the vertical lines are the dry bulb. Diagonal lines, wet bulb. The curvy lines is the relative humidity. Okay? One more. The other set of the diagonal lines is the enthalpy. Enthalpy is the energy that can be distributed or can be carried by the air at a certain amount of air. So the unit is kilojoule per kilogram of dry air. So you will see, if you go here, relative humidity, you would see the units. So here the units are there. See, 2%, 4%, 6%, 8%, 10%. Then this is 15%, then 25%. Then you will see here, this is 100%. This is 100% relative humidity. This is 50% relative humidity. This is 20, 30, 40, 50, 60, 70, 80, 90, 100%. So this is the relative humidity measured in percentage. You would see here the wet bulb temperature there, 30 degrees, 25 degrees, 20 degrees, 15 degrees, 10 degrees, 5 degrees, 0. And you would also see your dry bulb temperature measured in degrees also. This is 0, 5, 10, 15, 20, 25, 30, 35, 40. Then you would also see your enthalpy. Your enthalpy is here at kilojoule per kilogram of dry air. So you would see 10, 20, 30. You would also see the same numbers from here to here. These are the same. So this is 50 kilojoule, also 50 kilojoule. So this would help you make sure that you are using the correct diagonal lines. So if it matches here to here, so it gives you an assurance that you're using the correct diagonal line. You're not confusing it with a similar, almost parallel And there's the last volume of air. It's measured as grams of moisture per kilogram of air. Okay. All right. Grams of moisture per kilogram of air. So this is your humidity ratio. So this is 1, 10, 15, 20, 25. There's also vapor pressure here, limiters of mercury. But we're not going to use this vapor of measure in our AC system analysis. Question so far regarding the psychrometric chart? So again, there's the relative humidity, there's the wet bulb temperature, there's the dry bulb temperature, enthalpy, and humidity ratio. Next, we will go to our psychrometric process. All right, psychrometric process. So there are a few psychrometric process. So there's a cooling process, heating process, humidifying, and dehumidifying. These four are the main processes, are the main psychrometric process. Cooling process, heating process, humidifying, dehumidifying. Okay. If from one point and you have a psychrometric process, it moves this way, it's called heating process. You would see the dry bulb temperature, it increases from 30 becomes 45. So there's an increase in dry bulb temperature. It's a heating process. The opposite is the same. If you're at 30 degrees Celsius and it cools down from 30, it becomes 15. It's a cooling process. So when the point moves to the right side, it's a heating process. When the point moves to the left side, it's a cooling process. Keeping your temperature constant and the point moves upward, it's a humidifying process. The humidity ratio increases. If the point goes down, it's a dehumidifying process. But you could also mix these four processes together, giving you humidifying and cooling. So if it goes like this, it's humidifying and cooling. If you turn on your aircon, plus you turn on your humidifier for your essential oils, you're humidifying and you're cooling. If you turn on your aircon and you see the drain of your aircon going berserk, so there's a dehumidifying process. If there's no change in temperature, but you could see there's your unit is condensating, there's a dehumidifying process. Okay, so this same as the opposite. So you also have a dehumidifying heating and heating and humidifying. So the four main processes is the cooling, heating, dehumidifying, and humidifying. But all these processes, these two processes can be combined together. So how does this thing relate to our ACMV system? Okay, so we will have our sample calculation. All right. Let's say in our sample calculation, we want to design a room. A room is, regardless of the size of the room is designed at 21 degrees Celsius, 50% RH. Okay. So when you design a room, we estimate that the total heat load is 100 kilowatt. Okay. At 100 kilowatt, what is the size that we need for the cooling coil? How big is the cooling coil that we need? And what is the condensate drain water flow rate? This cooling coil will, in Tagalog, magpapawis, or will have a condensate. How much water will come out from this equipment, from this unit? All right. So we will try to calculate. We will try to check. Okay. First, define our points. Point 1, this is our room. So we will define our room condition. Point 2, our supply air condition. So what is the condition of the air supplying to the room? And 3, if it's coming from outside, what is the condition outside, outdoor air condition? Okay. In our example, in our previous example, we say the design is 21 degrees C, 50% RH. So how did we get this point? So from From our psychrometric chart, we can see here this is 20. The next line is 21, 22, 23, 24, 25. So at 21, go up, and then at 50% RH, the intersection, we will get this one. When we get this intersection, we know it's 21 degrees C, 50% RH. We can also get the enthalpy. The enthalpy is around 40 something. So using a psychrometric calculator, we can get 40.71 kilojoule per kilogram. And if you project this line going here, 5, 6, 7, about between 7 to 7.5. So we will get about 7.76 gram per kilogram. So we got this enthalpy and humidity ratio after we plot this 2150. 21 degrees Celsius, 50% RH. We get this intersection point. So from the room, it says there, we'll go back here. From the room, there, all this air comes out. So before it comes out, the air will come in. What is the point? What is the condition of this point 2? All right. Oh, sorry. Point 3 first, sorry. So outdoor air. Outdoor air is 33.2, 26.1. Now, this 33.2, 26.1 is the outdoor air condition given by the local authorities. Here in Singapore, SS553, they say that the outside air condition is 33.26. So I put 33.2, 26.1. Same, 33.2 from here, 33.2, I can bring up 26.1 from wet bulb here, 25, 26. So this is an intersection point. By having this intersection point, I will get my humidity ratio around 80, and I will get my humidity ratio around 18. So this is 15, around 18. Okay, this is 20, humidity ratio 20. So this is 15, it is about 18.5. All right. Going back to our condition. Latent heat load, the total heat load is 100 kilowatt. It says here 10% is latent heat load, which means sensible heat load is 90 kilowatt, 10 kilowatt is our latent heat load. If you for those guys that joined us in our ACMV series, the quotient of the sensible heat load over the total heat load is called the sensible heat ratio. All right, I will go back here, there. Sensible heat ratio. What is sensible heat ratio? The ratio between the sensible heat and the total heat. Now, you can see here, sensible heat over total heat. Okay? So, by having this sensible heat over total heat, we will get a 0.9 or 90% sensible heat ratio. Using this as our guide, okay, 90%, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So this line is 90%, or sensible heat and to total heat is 90. This line now is parallel to this line. Remember, we are using the psychrometric chart. We are dealing with the graphical use or graphical representation of the properties of air. So having 100% with 10% with 90 sensible heat ratio, we were able to draw this line to this line. Okay, so the angle of this line is same as the angle of this line. So this line and this line are perpendicular. Parallel. There you go. This line and this line are parallel. So your psychrometric process will have this graphical interface that will tell you what is the angle on each sensible heat ratio. Just for clarity and for to make our presentation neat, on the previous slides I took it out. Okay, but our psychrometric chart has this what do they call this? Protractor. There you go. Has this protractor. Okay. So now we are able to define our points. Point 1, point 2, point 3. Now, one guy before asked me, how come I put my point 2 here, right? So I will go back to this portion. All right, there you go. A cooling process and dehumidifying process can be performed individually. They cannot be performed together. So for example, our cooling process, when you cool an air, it will not dehumidify immediately. It will cool down first before it dehumidifies. So when the air is cooled down, it cools down all the way unto the saturation point until it goes down here. It follows this line. Okay, so which means everything that's coming out from the coil is 100% saturated. Okay, we need to remember that. Okay, on our psychrometric process, from outdoor air, it doesn't go this way. It doesn't go from 3 to 1. It goes here first, 100% saturation, and then it goes here until it reaches this point. So every time air comes out from the coil, and you can see there's a condensation taking part, it's 100% saturated with moisture before it goes to our room. So this is important, no? It's important to always know, always be worried that it always comes, that the air coming from the coil is always at saturation point. Okay, that's important. The air coming from the cooling coil is always at saturation point. This line is parallel to this line. This line, we get 90 because of the sensible heat ratio. Our example specified that the sensible heat ratio is 90%. No questions yet? Questions? If there's no question, wait, there's a question here. I would like to ask if you would communicate the psychrometric chart to the current respective engineering team to understand them logically. Is it using enthalpy or temperature? When relative humidity rises, what condition will? Okay, if the scenario when relative humidity rises, what condition will you explain for them to convince the respective design you're proposing in a certain condition room? Okay, noted, Sir Adrian. So as we go along, you would see on our psychrometric calculation how to manipulate these scenarios. So I'll continue first. Any other question? If there's no other question, I will continue.
Hi, Sir Danny.
Yes.
Where did you get the 9.98 degrees Celsius?
Which one?
Where did you
9.98, this one?
Yeah. Is it from the cooling coil?
Okay.
Or it's already distributed to the duct?
Going back. The condition after the cooling coil, here the AHU and the ducting are considered insulated. So whatever condition after the cooling coil will be the same condition before it comes out to your room. So all the duct loss is we did not consider the heat gain from the motor, from the fan. We did not consider. We assume that there's an adiabatic process, or it's insulated. So the condition after the coil is the same as the condition going out to your room. Okay? So we got the 9.98 degrees Celsius and 95% RH. We will get back to this 95% RH, no? But at the moment, we will say it's 100% saturated at 100%. We got this from the graphical representation from our design condition, point 1, drawing a parallel line. Then we got this point. So this point is not calculated. This point is arrived, or this point is derived from the line that we draw from here to here. Okay? So you would see, no, if you would go to your actual calculation versus your graphical representation, there would be some difference in your numbers, especially if you're using your formulas. Your formulas and your psychrometric chart will not 100% give you the same result, because we are using graphical representation. Sometimes your eyes will deceive you, so you will have a difference. So for example, here you would see 80 na nausog ko lang ng konti, or your pen slightly got disoriented, you would get 81. So which means all your calculation preceding that would be different already. So for example, here I put 80.81. Of course, our eyes will not see 81. We will see 80. Instead of 80.81, our calculation will be at 80 or 81, because a psychrometric chart is a graphical process. So if you use your formulas, of course you will get a different number, but it will be a similar number. For my experience, for example, I will get 200 kilowatt, but on my formula, I will get 198 or 188. So it will be roughly the same, but not exactly the same, or not even similar, but it will be within the range. Nasagot ko ba yung tanong mo, Sir Adrian? Was I able to answer your question?
Matanong ko lang sa, I'm good, but tanong ko lang, sir, kung yung, is this 9.98 is for Singapore setting or Philippines?
No. This 9.98 is a graphical representation from here to here. Noted. So nung dinrawing natin tong guhit na to, lumitaw tong 9.98. Ang Singapore condition, ito lang outdoor air. Okay?
Okay. Noted, sir.
So nung ginuhit natin tong from point 1 to point 2, parallel nitong guhit na to, lumitaw tong 9.98. Hindi to calculated. Nung ginuhit, lumitaw. When we draw this line from point 1 to point 2, then point 2 was determined. Alright? Okay. So now we have all these 3 points. What are we going to do with them? How are we going to calculate them? All right. Again, what we discussed earlier, the process from outdoor air going to your indoor air is not a straight line. It cools down first, going to the saturation point before it goes down. Then it goes down. It's not a straight line from 3 to 2. It's not a straight line from 3 to 1. But it goes cooling first, then after cooling, reaching the saturation point, it dehumidifies. That's why you will get condensation. That's where the water comes from. It dehumidifies. All right? Okay. So going back to our question, what is the size of the cooling coil? So from our using the room heat load data, we can require there you go. Using the room heat load data, we can determine, or we can calculate what is the required air needed to cool down the room. So this is your room setting. You know that it's 100 kilowatt for room heat load. What is the amount of air needed so that this room will be cooled down to 21 degrees. Okay. So using our formula, Q is equal to M delta H. M is the one that we're looking for. Q is the one that's equal to the room heat load. H is the change in enthalpy. So at point 1, the enthalpy is 40.71. At point 2, the enthalpy is 28.3. Their change in enthalpy, you remember our enthalpy unit is kilojoule per kilogram. Okay, kilojoule per kilogram. This change of enthalpy, if we know the heat load or the energy needed, the kilojoule, we can convert it into kilowatts. We know it's 100 kilowatts. So we will convert it 360,000 kilojoule per hour. So by using this 360,000 kilojoule per hour and this change in enthalpy, we will get the amount of air needed in kilogram. So using our formula, Q is equal to M delta H. M is the mass of air. We will get about 28,000 kilograms of air per hour. Using our air density, we will get 23,900 cubic meter per hour. So let's round it off. Let's say 24,000. So to cool down the room from 9.8 to 21, you would need 24,000 cubic meter of air per hour. Okay? So which means here in our schematic, you would need 24,000 air being pumped into the room so that it will cool down to 21 degrees Celsius, 50%. You need 24,000 cubic meter of air at 9.98 degrees Celsius to be inside the room, so it will cool down to 21 degrees Celsius. So now you already have your mass of air. Using this mass of air, you would need now to see how hard the coil needs to work. So from outdoor air to indoor air. For air to indoor air. Same formula, Q is equal to MH. MAH or M delta H. So now we don't know the Q, but we know we need 24,000 cubic meter of air. So using the difference in enthalpy, this enthalpy of the outdoor air is 80.81. The enthalpy of the supply air condition is 28.23. You get their difference. Change of enthalpy is 21.88 multiplied by your mass of air at 24,000 cubic meter per hour, change to kilogram. You will get about 416 kilowatt. So which means this coil is about 400 kilowatt. The size of this coil is about 400 kilowatt. We got it by calculating first what is the amount of air needed here, and using the amount of air needed here, we were able to determine the size of the coil using our psychrometric analysis, using our psychrometric chart. Okay. Question?
Sir Danny.
Yes.
Matanong ko lang sir if yung coil cooling yung capacity po ng coil should be greater than the heat load sa room?
Yes. So you would see the capacity of coil is 416. The heat load is about 100.
Noted, sir.
Okay. So Adrian is correct. The size of the coil is not necessarily the size of your heat load. Your heat load is about 100 kilowatt, but your coil, you could see in our calculation, is about 400 kilowatt.
Sir Danny.
All right.
Sir Danny, excuse me.
Yes, sir. Yes, sir.
Kapag po, halimbawa, na-design natin, exact 100, meron ka bang recommended percentage para tumaas yung coil cooling capacity?
Lakas-lakas ng konti, sir. Hindi ko marinig.
Kapag po pareho yung result, meron ka bang recommendation para tumaas yung coil cooling capacity? Meron bang pang, halimbawa,
sorry, hindi ko marinig. Medyo maingay yung background.
May maingay po yung, sir, yung ibang viewers ata.
Sorry, Adrian, paulit-ulit. May background noise, hindi ko naintindihan.
Yeah. May ano po kasi, may pumasok kong bago. Halimbawa lang po sir, yung result ng heat load is the same sa coil cooling capacity. Meron po bang ano tawag nito? Factor na i-multiply para po tumaas yung coil cooling capacity? Or
Okay. O,
yeah.
sasagutin ko yung tanong mo sa susunod nating slide. Alright? Okay. Ito, this one is your room heat load. Alright? This one is your coil cooling capacity or your coil cooling load. Like Adrian was saying, if the coil load is equal to the room load, which means the coil is only using this much. It's not using this much. So what is the scenario that your room heat load is equal to your coil cooling load? Okay. Your room heat load and your coil cooling load will be equal if the schematic is somewhat like this. If you take out this outside air, if this outside air is taken out, deleted, your coil cooling load will be equal to your room heat load. So depending on the scenario and depending on the application being used, no, your coil cooling load will vary greatly. So for our example here, okay, our example, the coil cooling load is a difference between 3 and 2. The room heat load is the difference between 2 and 1. So if I go to the different schematic, if I have 5 and 1 as my room heat load, 1 and 4, if I take out this 2 and 3, Adrian, if I take out this 2 and 3, 1 and 4, the difference between 1 and 4 is equal to the difference between 5 and 1. So depending on your application, or the size of your coil differs also. So if it's 100% recirculating air, then your room load and your coil load will be the same. But if you add in other factors like outside air, then your cooling load is different from your room heat load. Okay. Now we will have another sample. Now we have another question. The other question is, what is the condensate drain water flow rate? Okay. So again, this is our schematic. So from 3 to 2, the difference between 3 to 2, we need to know what is the flow rate, the water flow rate coming out here. Again, 0.1 is our room design condition, 0.2 is our supply air condition, and 0.3 is our outdoor air condition. Using our psychrometric chart again, outside air condition, we will get this humidity ratio. So at this point, we just project it horizontally, we will get this point. This point is about 18.5, so it was 18.55 kilogram per kilogram. Grams of water per kilogram of air. So our 0.2, the 9.98, when you project your line, you will get also 7.41 grams of water per kilogram. So this difference, this change in humidity ratio, gives you the amount of water coming out from your equipment. So previously we calculated at 24 cubic meter per hour. At 24 cubic meter per hour, using mass of water is equal to the mass of air times the change in humidity ratio. So our mass of air previously, 24,000 cubic meter per hour, changed to kilogram per hour. And the change in humidity ratio, 18.55 minus 7.51. There you go. Is equal to 11.14 gram per kilogram. So mass of water is equal to 28,000 kilogram times 11.14. It will give you an approximation of 5 liters per minute. So this air handling unit or this aircon is condensating or giving you a condensate water of 5 liters approximately 5 liters per minute. So you'll be able to determine your pipe size already based on this flow rate. Okay. So another example, another sample calculation. Now, earlier when we were calculating, we were assuming very simple. All the outdoor air goes inside the room, and the room after the room it goes out. Now we will have a return air. So here on this point, you have a mixing of two different conditions. So our condition previously, we will the same, 21 degrees Celsius, 50% RH. This is our design condition. Our total heat loads, we will keep it at 100 kilowatt inside our room with 10% latent heat load or what do you call this, 90% sensible heat factor. And now we are introducing 10% fresh air. So whatever air is needed here, 10% of it is outside air. So if 0.5, the supply air is 100%, return air is only 90%, then 10% comes from outside. So here, there's a mixing of 90% return air and 10% outdoor air. So what is the size of the coil? And what is the condensate drain water flow rate? Same question, but different parameters. All right. So now here, you can see 0.1, 0.2, 0.3, 0.4, 0.5. 0.1, 0.2, 0.3, 0.4, 0.5. All right, go back. 0.1, design condition. 0.2, outdoor air. 0.3, when the design condition, which is the return air, mixes with the outdoor condition, you get 0.3. Then this 0.3 is cooled down by your cooling coil, going to 0.4, then 0.5, then back to 0.1. Previously, we already determined this line, 90% sensible factor. Remember, parallel lines from our protractor. Okay. Now, this line, all right, when 2 points or when 2 conditions of air mixes together, from our instance, the outdoor air and the return air mixes together, the resulting condition will fall within this line. But which point is 0.3? How did we determine this 0.3? Okay. This 0.3 was determined because of this one, 10% fresh air. Okay. 10% fresh air. Going back to our psychrometric analysis, 10% fresh air. How do we get 10% fresh air? Okay, so 10% fresh air is 10% of this line. If you just imagine the 0.2 and 0.1 are in the tug of war. 0.2 is only 10% as strong as 0.1. So from here, it can pull up, 0.2 can only pull up an amount of 10%. So if you divide this line in 10 segments, this is segment 1. So this line, the distance from this point to this point is 10% of the distance from this point to this point. Okay? Did you guys get that? Because this is a graphical representation, the psychrometric process is a graphical representation, you can calculate it also graphically. Our condition requires us 10% of fresh air. So this is 10% fresh air. This is 10%, this line is 10% of this longer line. Okay? Clear, huh? So, when outdoor air and return air mixes together, this is the resulting condition, 0.3. So outdoor air and design condition mixed together, the resulting condition is at 0.3. So when you cool down at 0.3, it will cool down and then dehumidify. At the humidification process, again, 9.8 and 0.1. Now, here, why did I put 2 points here, 0.4 and 0.5? There. 0.3, cooling down, then dehumidify at 0.4. However, the 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 coil manufacturer gives you what they call a bypass factor. So what is a bypass factor? Bypass factor is the amount of air that are bypassing your cooling coil. Your cooling coil, if you say 24,000 cubic meter per hour is passing through your coil, not all 24,000 are being cooled down. Some of them are just passing through. There's no change in them. So your coil manufacturer will give you a number called the bypass factor. Usually this bypass factor is very small. Sometimes it's usually it's 0.001 or 1%. So same principle as earlier. This from this point to this point, this is your bypass factor. So for me, my bypass factor, I think this is about 5. If I'm not mistaken, is about 5%. So this 5% now here is the representation of the bypass factor. This small line here is 5% of this bigger line. But the bypass factor is not actually 5%. So you need to check your coil manufacturer. The usual bypass factor is about 10%. 10% or less. So it cannot exceed 10%. Some of the bypass factors that I've seen, the good ones, they have at 5%, 4%. So need to check your manufacturer. However, you could see we are using at 0.5 the 9.98. This 9.98 is actually at considering the bypass factor already at 100%. So when the dehumidification process, it will be at 100% saturation point. There you go. But using the bypass factor from this line to this line, we'll be able to move up a little bit. So this little bit of change gives you about 95% RH. So you can see our calculation earlier is measured at 9.98 dry bulb at 95% RH. Okay. So this is the point that I'm trying to get. When two air conditions are mixed together, you can get their mixed condition based on their graphical representation, based on their ratio and proportion. If it's 10% RH, 10% outdoor and 90% indoor, then you will get this portion. Based on their ratio and proportion, you can adjust this 0.3. Same goes with your 0.4 and your 0.5. This 0.5 or the 95% RH is also a graphical representation of the bypass factor given by your manufacturer, by your coil manufacturer. So earlier, our coil load is from 0.2 to 0.4. Now, our coil load now, because it was mixed together, it will be from here only. So from 3 to 4. So this is your coil load, the green one, and the purple one is your room heat load. So you can see back on our schematic, no? In our schematic, this coil load now is 90% of this one and 10% of this one. Earlier is 100% of this one and 0 of this one. But now you have 90% of this and 10% of this. So which means your coil is significantly lower, very much lower. So you can see here, previously the coil load is from here to here. Now it's just from here to here. So the change in enthalpy is significantly less. So what is our coil load? So from here to here, can you guys calculate what is the change? What is the coil load needed now? So assuming at 24,000 cubic meter per hour, what is the coil load needed for 0.3 to 0.5? So going back, no? What is the formula is equal to Q M times change in enthalpy. So first, what is the change in enthalpy? So we'll see at 0.3 to 0.5. Can you guys calculate? So by calculating 0.3 and 0.5, no, 44.72 minus 28.23, it will give you 16.49. 16.49 times our previous calculation earlier. There you go. Previous calculation earlier at 28,920 kilogram of air times 28,920. It will give you about 476,000 kilojoules divided by 3,600. It will give you about about 132 kilowatt. There you go. Any questions? There. Oh, there, 143 kilowatt. I saw some questions earlier. Let me just check. From Sir Eric again. How to determine the drain pipe size from the psychrometric? Sorry, there's no pipe sizing on the psychrometric, but the water flow rate you will get from the psychrometric chart. So the pipe size, it's a different pipe calculation. We will discuss that on the next topic. That's a good topic to discuss. How to check the drain pipe size. So the drain pipe size is plumbing works because it's unpressured or no pressure required on the drain pipe. It's open to atmosphere. So there's a different way of pipe sizing than the previous the chilled water pipe sizing. So if you would like, you could check the local plumbing code. On the pipe, I think I sent a pipe sizer chart on the previous training. Let me double check. Let me double check. Oops, I'll stop my screen share first. Stop. Oh, I did not send. Okay, I'll send you a screenshot here. Let me share my screen again. Share screen. Share screen. There you go. Share. So here, last time we discussed about the chilled water pipe size. I think on the sizing table that I gave you, there's a condensate drain pipe sizing table. So based on the kilowatt, you will be able to get your pipe size diameter. Please take note some local codes. Example here in Singapore, the 25 degree is 25 mm or 1 inch is the minimum. I think in the Philippines, some of the aircon installer there, they're still using ½ inch or 15 mm. So check on your local codes if what is the minimum pipe size required. All right. Thank you very much. Thank you, Sir Eric. Any other questions that I can get from you? I can answer. I saw a question by Ruel in Facebook. Is 9.98 the cooling coil temperature? Yes, the 9.98 is the off coil temperature. Cooling coil off coil temperature. So when the air touches the cooling coil, it's the on coil. On coil. And when it leaves the coil, it's called the off coil. So it's off coil temperature. The 9.98 is the off coil temperature. Any more question? If there's no more question, it's free to ask questions though. But if there's any more if there's no more question, again, thank you very much. This is the first of our new series, the ACMV Fundamentals. For those of you who are watching, this session will be recorded and it will be available both on Facebook and our Even Learning page and through the YouTube channel. My YouTube channel is Donny Gabriel. You can search that and it will be available there. Our next training will be in 3 weeks, February 20, ACMV case study. So design of a warehouse. It will be a premium training, so it won't be available in Facebook. It won't be available in YouTube. So it will only be available through Zoom. For those of you that are interested, be sure to see our Even Learning event page for more details and for registration. We would appreciate it if you help us improve our service to you by accomplishing or giving us feedback to our feedback form. The link is posted in the comment section. So wala na. Kung wala na, thank you guys very much. I appreciate you guys joining in and I will see you again in 3 weeks.